doing? Getting into this chapter 8. All right. We've been into chapter 8. I mean, we're getting into the vibrational motion. So I love this stuff. This stuff to me is so cool. I do a lot of vibrational spectroscopy, so IR spectroscopy in my research. So I love getting into this stuff. So let's do it. So up to now, we haven't really treated the potential energy in a very realistic sense as far as our potential energy operator and our Hamiltonian. We've given it cases where we've called it some constant V. We've given it cases where we've called it zero, where we've called it infinite. But now we're going to approach a potential energy operator using something borrowed from classical mechanics, which is Hooke's law. Okay, so a particle undergoes harmonic motion if it experiences a Hooke's law restoring force. Okay, and the idea behind that is to imagine we have two masses on a spring. All right. And so this particle, or these particles, if you will undergo harmonic motion if they oscillate back and forth on this spring, and their potential energy is described by the following curve. Okay, so we call here this x. We're going to really be calling x displacement. So that's important to know. So we've, in this case, x, it's really referring to as the total distance this thing has displaced. Okay, so this might be one level of displacement, right? Up at the higher end of the curve. But, down here at the lower end of the potential energy curve, we might have a lot less displacement. Okay. So what we have, so this Hooke's law restoring force is given by the following: force, right? Okay, equals negative kf times x, where kf is our force constant in terms of newtons per meter. And of course, then displacement will have units of meters. So that gives us the proper units of force in newtons. Okay. We also recall from Newton's laws, force equals dv by dx, negative dv by dx, okay, where that's potential energy versus change in position, okay? And so if we do a quick little divide and conquer situation here, where I'm going to multiply dx over to this side, and I've got negative dv on this side, okay? And if I integrate both sides, then, and of course recognizing that f is kf times x, right? So that becomes integral of negative kf times x dx, all right? And then, of course, the integral of dv just simply equals v. So now when we integrate this thing, this is where we get the 1/2, so negative and negative signs cancel. This is where we get the 1/2 kf times x squared. And you can see right here, so now that's going to become our potential energy operator, 1/2 times kf x squared. All right. And so now, if we consider also our boundary condition, okay, one of the boundary conditions, we know that psi has to equal 0 when x equals plus or minus infinity. So as given right here. And so what that means is our oscillator can't, be displaced by an infinitely large distance, right? We are going to build in for the fact that this thing can only oscillate or only be displaced by a finite amount. Okay, so that's where we'll say its potential energy will tend to infinity as we go up and up and up. All right. And so now if I build up the Schrodinger equation here, you all know how we do this by now. Look, we've got our kinetic energy term, okay? So I'll just say Ke, right? Where we know that's the negative h bar squared divided by 2m times second derivative of psi. And then now we can build in this, what I'll say, Pe, our potential energy term, using Hooke's law for harmonic motion, okay? And then, of course, all of that equals E times psi. So let's do it. Let's solve this sucker. Following our order of operation, cry, pray, guess, solve. So you do the crying and the praying. I'll do the guessing and the solving. And you can do the guessing and solving with me. So the first thing we're going to do, like we've always done, we're going to rearrange the second order differential equation in terms of the reduced form. Okay? So that's going to go as following. So first I'm going to multiply through negative 2m over h bar squared through. Okay? So let's go ahead and do that. So when I do that, I can now just write the second derivative in psi of x. All right? And now that's going to be minus, and so the 2's and the 2's cancel because I'm multiplying it through, right? So now it's going to be minus m kf over h bar squared times x squared times psi of x, okay? And then now I'll show you that all of that equals, because remember I multiplied through the negative 2m over h bar squared all the way through. So now I get negative 2me over h bar squared psi of x, like we're normally used to seeing, okay? And so now, of course, rearranging this for the reduced form, I can write, right, just we're going to set all of this equal to 0. So minus, let's see here, kf over h bar squared times x squared times psi of x. And of course, now that's plus 2me over h bar squared psi of x, all equal to 0. Okay? And so now you've noticed here that I've got a couple of cheater things. So this is standard, I guess not really cheater things, things to make writing our equation a little bit easier. And so these are just, I know that we use lambda for wavelength, so that's not what's going on here. We don't have enough Greek letters, okay? And you're also going to see there's something, a bit of convenience, where we're going to call y equal to the square root of m times kf over h bar squared times x, okay? And so the reason why we're going to do that is because you notice that I got these constants right here, mkf over h bar squared times x squared, right? So if we replace all of this now, you know, if we use this simple notation, then I can replace all of this with just y squared. And so what's going to happen, we're going to rewrite our Schrodinger equation in a way that we can get rid of all of these constants. And we're going to switch letters. Don't worry, there's a reason for switching the letters, and we're going to come back to that in more detail, okay? So I'm going to switch to using y. And I'm going to write here second derivative of psi of y over dy squared, okay? Minus, and now I'm going to replace this whole thing by y squared, psi of y. And then now you notice I'm also going to use this lambda here, this 2me over h bar squared for lambda. So we can say plus lambda times psi of y, all equals 0. And now this should, being the key word, be a lot more easy to solve, okay? And of course, what we also need to build in is that asymptotic relationship we talked about, right? As psi approaches 0, as x approaches plus or minus infinity. So we're going to need to have solutions for y approaching infinity, okay? And so what that means is we need some type of asymptotic relationship. And this is the point where we could go through our normal guess solve methods, right? Where we guess e to the, in this case, it'd be e to the ay. But as it turns out, that's not going to give us this y approaching infinity asymptotic solutions. Okay? And again, I'll remind you, asymptotic because, right, as this approaches infinity, we are going to have, some cutoff, right? Some asymptotic relationship of where we don't expect it to have infinite displacement. Okay? So what that means is our guess solution is slightly different than the guess solutions we've made before. And I'm also going to write this as a proportional or approximately equal to e to the plus or minus y squared divided by 2. So this becomes our guess solution. And this is kind of like the standard procedure in solving the harmonic oscillator problem. Okay? And so that gives us our E, all right? And what we're also missing to give it this asymptotic relationship here, we're going to say what we really need to get rid of this approximately equal to and make it a proper equality, we're going to say that we need some function in y, and then let's see, I'll say minus ey squared divided by 2. So we need this f of y. So this is a polynomial in y that's going to give us these asymptotic quantized values. Okay? And so the simplest thing I can describe here, so I've got on my Mathematica file, I've got a whole number of polynomials right here. All right? And what these polynomials give us are definite quantized values where, in this simple example, where the polynomial crosses the x-axis, right? So I'm going to point out this purple one, right? We can see that it's crossing the x-axis at definite fixed values, okay? So that's going to give us that kind of cutoff, that asymptotic cutoff for our large displacement. All right, so this is going to become our guess solution. Psi equals f of y e to the negative y squared over 2. And the standard procedure is to ignore the plus solution because this e to the minus y squared, as we shall see, that describes a Gaussian distribution, which is also going to help us get a physically meaningful solution. Okay, so this is kind of the point in the class where we couldn't do this. We would have to really grind away trying to guess at a solution for a long, long time. And that's kind of beyond the scope of the class. So our guess, that's the standard guess for this harmonic oscillator problem. Okay, so let's go for it. So I'm going to rewrite that solution that we've got to solve here. So I put it up here. Second derivative in y. And again, we'll address this transformation of coordinates soon. I don't want you to be too worried about it. For now, it just helps us kind of ease through the solution. Okay. And so let's see here. If my guess is psi of y equals f of y e to the negative y squared divided by 2, then this starts to become a mess, and I'll show you. So now, did I leave myself enough room? Yes, I got enough room. So first thing I need to do is take the first derivative of this, right? So I'll say d dy of psi of y. And look, you can tell that I'm going to have a chain rule situation, right? So first I take the derivative of the function. That's going to be f prime of y. And then times the other part of the function. And then now I've got to take the derivative of the exponential. And so that's going to be, it ends up just being minus y, right? So it becomes minus 2y divided by 2. So that's just minus y times f of y times e to the negative squared, e to the negative y squared divided by 2. Okay. Now, as you might guess, we've got to take the second derivative of this thing. And it's going to get hairy. So I have to take the derivative of the derivative, right? And so what we're going to have, let's make sure that I keep track of all my things on my cheater notes here. So first thing I'm going to do, I'll take the derivative of this term. So that's going to give me the second derivative of that chunk times the original function, e to the negative y squared divided by 2. And then now I've got to do the derivative of the exponential, which is going to be negative 2y divided by 2, or just negative y. So that's going to become negative y times f prime of y times e to the negative y squared divided by 2. Okay, now I've got to do the derivative of that second term. Okay, so now I've got a triple situation to deal with, right? So I've got y, I've got f of y, and I've got e to the negative y squared divided by 2. All right, so the derivative of y is just 1. So now that whole chunk is going to become minus f of y e to the negative y squared divided by 2. Okay. Now we've got to do the derivative of the function. So that's going to be negative y times f prime of y times e to the negative y squared divided by 2. And then finally, I have to do the derivative of the exponential. And so keep in mind, I've already got a minus y there. And so the derivative of this e to the negative y divided by 2 is negative 2y divided by 2 times e to the negative y squared divided by 2. So that becomes negative y times negative y, which becomes positive y squared. And then now we just keep everything together, f of y, and then e to the negative y squared divided by 2. Goodness golly, so there is just our second derivative. And we could inspect this really quick to see if there's anything that I can cancel or combine. So let's do that really quick. So here is, yep, 2 terms that I can combine right there. So that's nice. And then what else can I combine? Let's see here. Okay, so let's keep track of this. Let's keep this going. So I'm going to say now all of this equals. And then another thing that I'm going to do, you can tell right away that I can factor out an e to the negative y squared divided by 2 out of all of these terms. So I'm just going to do that straight off the bat. Okay. So then I would have my second derivative, right? Okay, times the exponential. And then now, so I can combine these two things, negative y, f prime of y e to negative y squared. And that's just going to become negative 2y times f prime of y. And then I've got the exponential right there. So let's see. So then now I've got to deal with this f of y right here. So I'm going to cross these off so I know that I've dealt with them. Okay, so I've done all 3 of these. So now I've got that term, and so that's just going to be minus our function in y. Okay, and then so I took care of that. And then finally, we've got to take care of that, which is now going to be plus y squared times f of y. And so I'll remind you, right, this is just the second derivative inside. That's all we've done. We haven't even put it through our Schrodinger equation yet. Oh, man. Okay, so let's do that. So when we do that, we get the following. So we've already got the second derivative, so there it is, right? So I'm just going to rewrite all of that as the following. I'm going to say, let's see. Oh, you know what? Do I have a whole nother page to deal with? I got a whole nother page to deal with. So great. So let's do that. Okie dokie. And I'll just remind you up here once again, our Schrodinger equation that we're trying to solve, minus y squared, or excuse me, this is really just our, the reduced form plus y psi of y equals 0. Okay, so let's keep it going. So our second derivative of psi, that was the big function where that's going to be f double prime of y. minus 2y f prime of y minus f of y. I skipped writing a term. So this will just be slightly out of order than the previous slide, but that's okay. So those are the two terms I wrote out of order. So then now that's all times e to the y squared divided by 2. Okay, so just this is our second derivative, right? Now we've got to say minus y squared times our psi of y. And remember, our psi of y, we guessed that it was some function f of y e to the negative y squared divided by 2. Alrighty, so that's now y squared times f of y e to the negative y squared divided by 2. So that takes care of this middle term. And then now finally, that's plus lambda times f of y times e to the negative y squared divided by 2, all equal to 0. And so let's see here. Is there anything we can do to simplify this? So we inspect once again. And oops, I forgot to put, so I'm going to make some much bigger parentheses around this thing, right? So remember, this is e to the negative y squared times this whole chunk, okay? And so if we look at anything that we can cancel, yes, brilliant. Look at this. I've got the y squared and the y squared terms, and those will cancel out. So that's great. So now I can say f double prime of y minus 2y f prime of y minus f of y, and all of that is still multiplied by e to the negative y squared divided by 2. And so now that chunk goes away. So then now this is just plus lambda f of y e to the negative y squared divided by 2. And this is something, reasonably we can work with, right? As you can tell, if we keep going with this thing, I could even cancel the e to the y squared divided by 2, okay? So we can cancel those out, and we can keep simplifying. F double prime y minus 2y f prime of y minus f of y plus lambda f of y. And then now to simplify this even further, we can combine terms with the f of y. Okay, and so that's going to get combined as lambda minus 1 times f of y, so there's a plus there, all equal to 0. And now we still haven't solved the thing, but we've got it in a much more reasonable form. Okay, so we have, right, let's just kind of go through this again, and I'm going to box this off. So it's still not solved yet. All right, so what do we got to do to solve it? Well, we recognize that we need some function, some polynomial, second derivative of that function. We need then obviously the first derivative of that function and then just the function. And it has to satisfy this relationship. Okay. So the general solution of this, we know that f of y has to be a polynomial. So our general solution for that polynomial, I'm just going to set this up as the general form of a polynomial, which says the sum of all terms a y to the power nu, where nu is going to be my polymeric term that I can keep adding on. So for example, if nu is equal to 2, then I would have some polynomial that says, a y squared plus a y plus a, right? Or if nu is equal to 4, I would have y to the 4th power plus y to the 3rd power plus y to the 2nd power, etc. So I would get these polynomials, okay? And so as it turns out, there is a very special solution. So this is the equation that I just spent all that time deriving, okay? And here is that general solution. As it turns out, there's a very special relationship that satisfies this equation, and it's called the Hermite polynomials, okay? And so here you can see how they're written, so let's just compare this. So the Hermite polynomials are given as h of nu. Technically, h nu of y is how the function's given, okay? But here is the special relationship. Look, it's the second derivative, minus 2y times the first derivative, right? Minus 2y times the first derivative. And then now in this term, it just says plus 2 nu times the function. And here we've got this written as lambda minus 1 times the function. And that's because that lambda is a big collection of all of our constants. And as we shall see later on, when the solutions become normalized, we can relate all of those constants to that quantum number. I'm not going to worry about going down that rabbit hole any further. But what I will say is the following. So once again, the Hermite solutions satisfy this polynomial. Okay, they have a very special property where if we look at, so that says h prime of, h of nu prime, and that says h of nu, e to the negative y squared dy. So this is a really important integral property, okay? If nu prime is not equal to nu, this equals 0. So in other words, the Hermite polynomials are orthogonal to each other. Fantastic. So that's one requirement of wave functions anyways, okay? But if nu prime equals nu, so if we're talking about the same state, we get a numeric answer, which is awesome. That's another thing that we need out of this, okay? And also there's, I'm not showing you like a predictor of how these Hermite polynomials come up. Here you can see what they are, all right? So this general solution, doesn't quite kind of show you how these all expand. But that's okay, because I want to show you something. There's a really handy trick in Mathematica. Mathematica has all the Hermite polynomials built into it. Of course it does. And so here's how the code works. Here's how it goes. You type Hermite H bracket, okay? That little 0 there, that is in reference to the quantum number nu, okay? And so by the way, right, let's write that down. Quantum number, we see the emergence of a new quantum number, nu, the new quantum number, nu. And so basically we can start thinking of these quantum numbers as these quantized integers that give us the quantized solutions to the Schrodinger equation, okay? So that quantum number nu, that is satisfying our Hermite polynomial solution here for this equation, all right? And so just to show you, Mathematica, right, has these things built in, which is really cool. So if I say 0 and y, look, it just gives me 1, and that's the Hermite polynomial for nu is equal to 0. It's just 1. But check it out. If I make nu equal to 1, then look, I get 2y. If I wanted to keep this in terms of x, I could change that to x and it becomes 2x. We're going to stick with the y because I'll remind you that y contains all of those constants that we ignored, okay? So if I go up to quantum number 2, look, there it is, 4y squared minus 2, and there it is. If I go all the way up to 6, lovely, there it is. So that's awesome that the Hermite polynomials are already built in there, okay? So we still don't have a solution to the Schrodinger equation. We only have a general solution, and that is the Hermite polynomial, okay? So what is the full equation gotta be? All right, well, I'll remind you, we guessed way back up here, let's see. Yes, here it is. We guessed, right, that our solution was going to be some polynomial f of y times e to the negative y squared divided by 2. Okay, so remember that. This f of y, that's a Hermite polynomial, okay? So what we're going to have in our Schrodinger equation is a Hermite polynomial, this exponential to the negative y squared divided by 2, and, of course, we need a normalization constant. So that's where I have this all written out right here, right? So I'll remind you, f of y we said was, or excuse me, psi of y was f of y e to the negative y squared divided by 2. So there that is, where I'm going to replace f of y with my Hermite polynomial in y. We've got there the e to the negative y squared divided by 2. And then finally, we've got a to be determined normalization constant that, as it turns out, is going to be also a function of quantum number nu. Okay, so now what I want to show you really quick here, this gets kind of confusing because here you see this is written as psi of x, but now we have this written as h of y, but now this is written as e to the negative y squared divided by 2. Okay, well, here's all of those constants that we collected, all right? And this is standard to give them in the 1/4 power. And the reason for that is because if we were to go and do a unit analysis on all of these constants, we would actually get that this alpha term is meters to the 4th power. So by taking the 1/4 root of it, we get units of meters. And then now check it out. Our y equals this x divided by alpha, where once again, that was a collection of all of those constants, okay? And so now when we see these functions in terms of y, our y scale becomes unitless. So we can kind of, and that y scale is still the displacement scale, right? I could still think of this displacement in terms of y. However, when we use that y, this distance is unitless and it is scaled by the alpha constant. However, if we wanted to actually do this in proper units, okay, then any place we see a y, we replace it with x divided by alpha, all right? And then we will actually be calculating the wave function in actual, units of displacement, okay, in terms of meters if we used, all of our standard notation. So for example, if I wanted to now continue writing this psi of x, okay, I'm still going to have this, to be determined normalization constant. But now when I rewrite my Hermite polynomial, I've got to rewrite it not as h of y, but rather h of x divided by alpha, okay? So over here, right, in my Mathematica, I could replace that with, I'm just going to say x divided by a, okay? And yeah, I would have to do that in my polynomial because that's going to help me properly take into account all those units that we dropped out, okay? And then also, this is no longer going to be an e to the negative y squared divided by 2, okay? Rather, it's going to be an e to the negative x squared divided by 2 times alpha squared, all right? And now I can think of my wave function only in terms of x, which is convenient based on, that we always like to think of this scale as the x scale. Okay, and the last thing that I'm going to point out in this lecture, and I'm just kind of shortcutting. I'm not showing you that we get directly to the result for energy, right? But remember, we sought out to solve the Schrodinger equation Hamiltonian as a function of quantum number nu now, psi of nu, that equals E of nu times psi of nu. So here is our energy solution, which goes as E equals nu plus 1/2 times h bar omega. So it's a lowercase omega. And that's not operator omega, it's just the Greek letter omega. We don't have enough letters. So what is omega? Well, this is what we call the oscillator frequency. And that oscillator frequency is given by the square root of the force constant divided by the mass. And so what's really cool about this solution here, what I'm going to show you now, okay, what we predict in this model all of these different quantum numbers when we put them in there. So for example, the first one is 0. We still have an energy level that's at 1/2 h bar omega. Okay, well, what about if nu is equal to 1? Well, then that next level is at 3/2 h bar omega. Well, what if nu is equal to 2? Well, it's 5/2 h bar omega. And so what you'll notice here, as indicated by this picture, the energy spacings are linear, so they're the same as you go up, and they have values of h bar omega. Well, why is that cool? Well, remember back in your Gen Chem days, E equals H times nu, right? Which equals HC over lambda. Well, look at our solution. Our solution is H bar times omega, but that's still Planck's constant times frequency. Really, really cool that it comes out like that, okay? So our oscillator frequency, right, that's going to have units of 1/seconds. We know H bar has units of joules times seconds. So this is perfect. This is a really cool result. I think it is. Okay. So I've been talking for about 36 minutes, so I'll cut it off here. Coming up next, we're going to normalize this wave function and actually find out the normalization constant. Okay. And as you can also see from my Mathematica file, I've got calculations of alpha here. So where I'm actually going to show you what happens when we apply real numbers into this whole alpha thing and how it sets our scale for displacement. Okay, folks, I'll see you in the next video.